Welcome back all of you. In the last few lectures, we were dealing with critical state soil mechanics. If you have noticed, we have been adding certain important informations one after the other. And lastly, we discussed about soil yielding. Now, where are we heading to? We are heading towards defining a state boundary surface for the soil. And when I say boundary surface, it means the domain within which the soil would exist. Soil would exist mechanically. Mechanical means because of its mechanical response, otherwise soil is always there. Now, whether soil would exist as a load bearing medium when it is subjected to shearing, that is what it means. So, when we say boundary surface, we are trying to understand the limit within which the soil would exist during shearing as a load bearing member. Now, for that we need to define a limit within which the soil may not exist, and one possibility was in terms of soil yielding. So, yielding is a good indication that yes, soil is going to be in severe distress, that is plastic deformation starts setting in. And we have seen in the last lecture that as the yield stress yield curve progressively increases, it reaches a point where the yield curve meets the effective stress path and the critical state. So, though that particular yield curve which passes through the point of intersection of effective stress path with the critical state line, that particular yield curve happens to be the final boundary. During the expansion of yield curve, that defines the final boundary. Now, we have understood it physically. Now, for any engineering application, we need to define it mathematically. So, there need to be certain models based on which the yield curve is defined. So, in today's and the upcoming lecture, we will see how yield curve is defined mathematically based on two popular models, which is based on critical state framework. So, the first model is Camp-Clay model, which we will see in today's lecture. I would also like to mention here that in this particular course, you will not be studying all the aspects of such a model or critical state framework. We are basically understanding the concepts in stress parameters in terms of stress variations, rather mostly applicable for stress path. We are not in a position to gain more knowledge from the strain point of view. I mean to say, when I say strain, elastic strain and followed by plastic strain, a bit of it we will be discussing in the next module, next lecture I mean. So, here what we are understanding would be the basic understanding which is needed further for understanding the plastic response. So, with that let us try to understand what is a Camp-Clay model today, and with that understanding we will move on to the next model, and possibly you will be able to appreciate why we will not be able to deal the entire aspects in this particular lecture. So, the first model is the Camp-Clay model. Now, the name suggests that it is a kind of clay or something like that. It is not so. I would strongly recommend you reading Schofield and Roth's book wherein it is stated that Cam is the name of the river which flows besides or close to Cambridge University. Now, clay is here clay in the sense it is not meaning a kind of particular clay maybe which is obtained from there. It is not like that. Cam clay is a generic name for that particular model. It has nothing to do with the clay response. It has something to do with the theoretical model which they have developed, and they wanted to make it a more generic name in nature. So, that is why such a name, which is Cam clay. Now, as I already told, defining state boundary surface is important. We are heading towards that. Now, there are different ways by which you can define the state boundary. Some of them we have already seen. We have seen a peak line, that is also a state boundary, that is a part of state boundary. We have seen the yield kind of curve in the last lecture. We have seen the tension cutoff zone. So, these are all fragments of state boundary. Now, there can be a specific shape and model based on which we define this, that is also a state boundary. So, there are different ways by which the state boundary surface is defined. This state boundary surface gives the domain within which soil state can exist during loading. So, this later part of the sentence is important. We are discussing the existence of soil state during loading, otherwise soil is very much there. We are not bothered about that existence, whether the soil will be able to bear its load without failure. The normally consolidated line, the peak line, we will see this normally consolidated, why it becomes a kind of fragment of SBS, that we will see later. Peak line we have understood clearly. Tension cutoff zone, that also we have understood. We know that nothing is going to be there towards the left end. Of course, in normally consolidated in VP dash plot, we have already seen that it is the rightmost boundary. So, in that sense, that is also a state boundary surface. And yield curve, specific yield curve. When I say yield curve, not all the yield curves, because yield curve can expand in its size. Is a final yield curve where I told already which passes through the point of intersection of effective stress path meeting with the critical state line. These are all fragments of SBS. Now, we will see, we will put all these facts together and finally understand what is a kind of state boundary surface in 2D as well as in 3D variation or the framework. Mathematical representation is needed for SBS, then only it will be useful for engineers. This is possible. Now, what is possible? Mathematical representation is possible by fitting equations to experimental data, developing purely a theoretical framework based on mechanics, or the combination of two. Now, the biggest challenge is how good the framework represent the real soil behavior. Now, this is asking for more, like we are trying to mathematically quantify something which is beyond our imagination, and that is soil behavior. We have to admit the fact that in spite of all our knowledge and development, still there is a gap in understanding the actual soil behavior. So, a particular model which may work very well for a specific type of soil and situations may not work for another type of soil in the same situation, or for a different situation it may not work for the same soil. So, there are different possibilities. So, we cannot generalize a particular model, but how close, we are not looking for 100% matching, how close the given model is with respect to the actual or the real soil behavior, that is what the biggest challenge is. So, there is always a trade off between simplicity, which is essentially needed for computational ease, and adequacy. how good it represent. So there is always we need to balance this. If we want to clearly model every bit of aspect of the soil, that is going to be computationally highly intensive, and that may not be really advantageous from a design perspective, where there are equally good amount of uncertainties otherwise also. So we need to strike a balance between how simple our model is vis-a-vis how good it represents. So that is why simplicity and adequacy. One of the basic constitutive models based on critical state framework is the Cham-Clay model, in short CCM. So we will now try to understand the critical state model, Cham-Clay model, which is the primary development. This is the original Cham-Clay model, and then it was modified a bit, and that is known as modified Cham-Clay, which we will see in the next lecture. So let us start with Cham-Clay, understanding Cham-Clay model. All the understanding which we have till now related to 2D representation of critical state and soil yielding becomes handy in understanding the Cham-Clay model. Without knowing that, it becomes difficult to appreciate what is Cham-Clay model. So that is why we have grown, or we have dealt the lectures in steps, adding one information one after the other. So I would strongly recommend that you have to go through the previous lectures before starting understanding this Cham-Clay model. This was put forth by Schofield and Roth in 1968, which is the original Cham-Clay. Soil is assumed to be frictional. Essentially, it is assumed to be frictional. Soil state boundary surface is taken as the yield surface, or the yield curve in 2 dimension. It is very easy for us to understand this particular concept. It is a bound which we have seen, and that can be used for defining the boundary. Plastic hardening related to plastic volumetric strain. Now I would be a bit cautious in using these terminologies in this particular course. The very reason is, we are not discussing anything important or in depth about the plasticity behavior of soil. So here plastic hardening, whatever the expansion of the yield curve, is basically related to the plastic volumetric strain. You remember the V versus P dash plot, where the normally consolidated line, it moves along the normally consolidated line. So every time it moves, we have seen in the last lecture, the size of the yield curve would increase. So basically the plastic hardening is related to plastic volumetric strain. Now there is another kind of strain that is going to take place, that is shear strain during loading. So that part is also there. Unfortunately, we will not be able to discuss those in detail. Different models in Cham-Clay differs in terms of the equation used to represent the yield curve. So basically the difference between different Cham-Clay models in the same Cham-Clay family is the kind of yield curve that is used. Otherwise, the kind of critical state concepts that we use in all these models are pretty same. In original Cham-Clay, the yield curve is logarithmic spiral. Because of the closeness in whatever we have seen, the kind of boundary that we have seen, logarithmic spiral happens to be closer, and that is why for Cham-Clay model, that shape is adopted as the yield curve. So it looks something like this. It is in Q P dash plot. The yield curve is shown in this manner. So this is the yield curve. Now this is the logarithmic spiral yield curve. Now for completeness, we have shown for compression as well as for extension, but in our subsequent lectures we will be basically concentrating on the compression portion. So that is one half of the yield curve. In fact, the yield curve is mirror image on both sides, in compression as well as in extension. So we will be basically dealing with positive value of Q. The logarithmic spiral shape may not be convenient for numerical modeling. You can see this particular portion wherein there is a pointed edge here. Now, for all numerical modeling we need to ensure the continuity of the differential equation which is used. So, basically here this particular location, it creates problem in some of the numerical models and it's the stability of the algorithm. So, for that reason, that is the reason why the modification has been given, but to understand the basics of CAMCLA, we need to understand this particular model, original CAMCLA also. So, it may predict unrealistic plastic shear strain increment. Now, again I would like to use this particular word with caution, because we are not discussing this particular term, the plastic shear strain increment. It is basically relevant to plasticity behavior of soil. So, there is an issue that it can predict, because of this particular model can predict unrealistic plastic shear strain increment. So, let us understand what is the mathematical representation of CAMCLA model yield curve. Let us consider a specific volume of Vi. So, this is QP dash plot and this is VP dash plot. Now, let us consider the reference Vi. So, this is the Vi corresponding to which there is an initial consolidation point which is Pi on the ICL NCL. Now, this can be either isotropically or it is one dimensional consolidated point Pi, for which the specific volume is Vi. Now, let us try to understand it in QP dash plot. Now, this is the initial point Pi. Logarithmic spiral curve corresponding to this particular point. Now, we have already seen in the yielding lecture that the extreme point is given by this pre-consolidation pressure. Now, for this particular case it is Pi. So, the extreme point of the yield curve Yi will be Pi. So, we need to fit a logarithmic spiral Yi, which is the yield curve corresponding to Pi. Now, yield curve Yi correspond to a specific volume Vi. Now, we need to understand that this particular yield curve is specific to this particular specific volume Vi. Now, as the specific volume changes, which means P is going to change. So, let us say if it is above or below, the kind of Pi will also change. Now, when Pi change, that means that the yield curve also changes. So, now for the time being, we need to understand that a particular yield curve is associated with a given specific volume, or we can say that this particular yield curve represents a kind of undrained behavior. What is undrained behavior? Where V is not changing. So, it is both ways true. If I say that yield curve corresponds to a given specific volume, or this particular yield curve represents a kind of undrained behavior, both explanation is same. Point on critical state line is Ci. So, let us say for this particular Vi, the point on the critical state line is Ci. Now, when you transfer this, how will it look like? Now, this part is very important. Now, when we transfer this particular point, it looks like this, that is the point where the critical state line meets the top portion of the yield curve. Top portion means the extreme top portion. So, that is Ci. So, this relationship one should keep in mind. Let us consider another specific volume of Vj, which is lesser than Vi. So, this is Vj. Now, the yield curve corresponding to this will be Yj, and the points will be Pj and Cj. So, this is Pj, that is taken to the QP dash plot, and this is Cj. So, that Cj will lie on the critical state line, and the kind of yield curve will be like this. Now, yield curves are identical in shape with different size. The shape of these two yield curves are very close to each other, but the shape differs depending upon whether it is Vi or Vj. So, it is apparent that there will be a family of different yield curves. Family of yield curves defines a closed boundary surface. Now, this, how does a closed boundary surface look like? I am not showing it here, we will discuss when we discuss about the state boundary surface. We need to imagine that there will be different family of such yield curves leading to a complete boundary surface in a given 3-dimensional space. This closed boundary surface is called the state boundary surface. Again, we will see about state boundary surface bit later. Only when we understand this Camclay and the prediction clearly, we will understand the state boundary surface. Okay, so we have understood the basic framework, and now the equation of state boundary surface or yield surface, that is how do we represent this particular yield curve, the logarithmic spiral yield curve is given by this expression, which is q by m p dash plus ln p dash upon p dash ci equal to 1, and here we are taking the condition q greater than 0, that means on the compression. Now, q we know, m is the slope of critical state line, which is again a critical state parameter, fundamental parameter. P dash we know, ln p dash ci. What is p dash ci? P dash ci is the effective pressure corresponding to this particular point ci. So, it will be somewhere here. So, that is also known. So, whatever is needed is known from this particular equation equal to 1, and for the condition q greater than 0. So, this is p dash ci, this one. Now, the main features of yield curve, that it should pass through origin where q axis is the tangent at that particular point. So, that is clearly visible here. You remember when we discussed about the last few lectures, we discussed that it is better that the failure envelope passes through the origin, because every time we cannot ensure the existence of cohesion. So, that is why in this particular framework we have already seen that it is purely taken as a frictional material. So, it passes through the origin with q axis as tangent. Zero gradient at critical state. Now, at this particular location Ci and Cj, what it means is that there is a zero gradient. If I draw a tangent at the topmost portion, it is horizontal. So, it is zero gradient at critical states at these points Ci and Cj. Vertex is at Pi and Pj, and that happens to be the extreme point of the yield curve on the right side. It also follows this important relationship, that is ln p dash pi upon p dash ci, that is the relationship between this point, the extreme point, and this point of intersection, that is the mean stress at this particular point and this particular point is related. And what is the relationship? It is ln p dash pi upon p dash ci is equal to 1, or if you take the anti-log, it is p dash pi is equal to 2.718 p dash ci. So, this is one attribute, one of the attributes of this particular yield curve. Similarly, if it is p dash j, it will be ln of p dash pj upon ln upon p dash cj is equal to 1. So, that relationship also holds. Now, how this relationship is coming, we will see in the subsequent slide. The yield curve defines all the permissible equilibrium state for soil with Vi. So, all the possible condition is governed, or it is taken care of by this yield curve. Now, CCM follows the normality condition. The critical state model follows the normality condition. And what is normality condition? Again, this has to come from the discussion of plasticity behavior of soil. Now, if somebody is interested to know this more, I strongly advise you to go through the plasticity behavior of soil in the specific textbook. Especially you can refer to the textbook by Potts. So, what is meant by this? It means that the plastic strain incremental vector is normal to yield curve. So, in the last lecture also we have seen that it is perpendicular. It means that now if I start discussing this, our designated portions is going to suffer. So, I cannot get into the details of plastic behavior. Now, let us again start with, I am referring to the same equation here. Let us start with this particular equation, q by m p dash plus ln p dash by p dash ci equal to 1. So, we will start from here. This is the yield curve and this is ci, pi, and this is marked. Now, we have understood one part. Now, we are slowly adding another part here. What is that part? That is the unloading line or the elastic component line. Where does it fall with respect to whatever we have discussed? In the last slide, we have not introduced this unloading line. Now, you can see that pi is here. This particular point ci is nothing but the point of crossing where this unloading line is crossing the critical state line. I would not say that it is touching, it is only notional in this particular plot Vp dash. It is the point where it is crossing. So, this particular point corresponds to Ci. So, what is the relationship? That is what we are trying to understand. So, when we understand Cham-Clay model, we need to keep these aspects in mind. So, then only it will work. So, Ci is the point where the yield curve intersects the critical state line, and that is where what it is shown here. Now, here you need to also see that this particular line, the unloading line, represents elasticity. The yield curve also defines the domain of elasticity. So, that is the point here, the crossing point is Ci. Now, q by m p dash is equal to 1 minus ln p dash by p dash Ci. I am just expanding it, 1 minus ln p dash plus ln p dash Ci. So, I am just expanding this ln. So, here you can also designate this particular point as Vf. Why? Because that is the point where the effective stress path would meet, and this any point on the critical state line can be considered as the failure point or VCS. Both are same. If we consider Vf, we understand that it is the failure point and that corresponds to VCS as well. So, now this is a point that Ci is a point on the critical state line. So, designating it as Vf holds good. It also means it is P dash F. Now, P dash F is same as P dash CS. Now, from this we can always write Vf is equal to V kappa minus kappa ln P dash F. Why? This is the point and that point lies on this particular line as well here. Now, how do we represent this particular loading unloading line? Again, refer back to our critical state discussion, wherein we can write this particular line as V in general. Any point on this loading unloading line can be written as V is equal to V kappa minus kappa ln P dash. Now, here for this particular specific point we can write Vf is equal to V kappa minus kappa ln P dash F. So, that is how it comes. We can also write the same point because it is lying on the critical state line. Now, how do we represent critical state line? V is equal to gamma minus lambda ln P dash. Now, here we know that it is always P dash F because it is lying on the critical state line. So, similarly for this particular point can also be designated as Vf is equal to gamma minus lambda ln P dash F, this particular point. Now, we can see this both represents Vf, we can equate it. So, gamma minus lambda ln P dash F is equal to V kappa minus kappa ln P dash F. Now, if you rearrange it, bringing this on the side, we can write gamma minus Vk, V kappa is equal to, if you bring it on this side, we can write ln P dash F into lambda minus kappa. So, then ln P dash F can be written as gamma minus V kappa upon lambda minus kappa. So, we got an expression for ln P dash F. Now we know that P dash Ci is equal to P dash F, the same point. This is P dash Ci, it is same as P dash F. Okay, so now we have got an expression for ln P dash F. Substituting that here, we can write Q by m P dash is equal to 1 minus ln P dash plus gamma minus V kappa upon lambda minus kappa. Now what are we doing? We know one expression which represents the yield curve. We are just trying to represent the same equation in a more general form involving the critical state parameters. So Q by m P dash is equal to 1 minus ln P dash plus this. Now V kappa, again we know V kappa is not a fixed parameter, it depends upon where the unloading has been done. Again we have discussed this point. So we need to replace V kappa. So how do we replace V kappa? Now we know that Q by m P dash is equal to, we can expand this, lambda minus kappa minus lambda minus kappa ln P dash plus gamma minus V kappa upon lambda minus kappa. Now we need to replace this V kappa. So we know V is equal to V kappa minus kappa ln P dash. Again the equation for this particular loading unloading line, from which we can write V kappa is equal to V plus kappa ln P dash. So we can substitute for V kappa. So when you substitute it, the first and the second term remain same, gamma minus V, that is given, minus kappa ln P dash. So we are substituting this to here. So then if you expand it, then we can write lambda minus kappa minus lambda ln P dash, this one, and then minus of minus will become plus kappa ln P dash plus gamma minus specific volume V minus kappa ln P dash. So this and this goes away. So after simplifying, we can write Q by m P dash is equal to 1 plus gamma minus V upon lambda minus kappa minus lambda ln P dash upon lambda minus kappa. So equation of state boundary surface in terms of all the critical state parameters can be rewritten as Q upon m P dash, this comes on the left hand side, lambda upon lambda minus kappa ln P dash minus gamma minus V upon lambda minus kappa equal to 1. So this is the equation for the yield curve which is represented by Cam Clay, original Cam Clay model, and you can see that lambda, kappa, m, these are all the critical state fundamental parameters of soil. So what we have done, we have defined the yield curve in terms of fundamental soil parameters which is coming from the critical state framework. So this is one part of the story, and in this particular course we will be discussing only this part of the story. What is the other part of the story? The other part of the story deals with the plastic straining, where we need to define how the plastic straining happens and how it propagates. So that particular aspect we are not discussing in this course. So here m, lambda, kappa and gamma are soil specific parameters. The yield surface correspond to constant specific volume, we have already discussed that. This would correspond to undrained stress path. Why? Because it is corresponding to a constant specific volume. So it is as good as telling it corresponds to a undrained stress path. Now equation for undrained stress path we can also derive, substitute for V equal to gamma minus lambda ln P dash Cs, which is the point of intersection of undrained stress path or yield curve with critical state line. Now this is the particular point. Now if that is considered as P dash F or P dash Cs, and for this particular V we substitute this equation gamma minus lambda ln P dash Cs, what we will get? So, we get q by m p dash plus lambda upon lambda minus kappa ln. Now, if you substitute for v here, so we have gamma minus gamma, here it will be plus lambda ln p dash cs, p dash cs. P dash cs. Now, gamma gamma goes away, it is plus ln p dash cs minus will become minus lambda ln p dash cs. Now, that when we put it here, we can write it is the same lambda by lambda minus kappa. So, here it will be now lambda by lambda minus kappa, and in that case we can take this particular parameter outside, then it will be ln p dash minus ln p dash cs. So, that will give ln p dash upon p dash cs, which is equal to 1, and it can also be written in this particular form because we know that it is corresponding to a specific volume. So, this is p dash y, that is the yield stress. Now, considering this to be yield stress, we will also see like this is the same equation. We will start from the same equation because we need to find out the relationship between p dash y and p dash ci. So, for point pi, so this particular point pi, q is equal to 0. At this particular point, q is equal to 0. Also, if you see here, this the same point, if you consider here p dash y, this is considered to be Vy corresponding to that particular yield. We can write Vy is equal to n. What is n? N is the point on the normally consolidated line corresponding to unit pressure, which we have already seen, minus lambda ln p dash y. So, specifically for Vy we can write, so V is equal to n minus lambda ln p dash. Now, for this particular point we can write n minus lambda ln p dash y. So, that is what is written here from the normally consolidated line. Substituting this in the state boundary surface equation or the yield curve equation, q is 0, lambda by lambda minus kappa ln, here specifically we are dealing with this particular point, so it is p dash y. So, p dash is equal to p dash y minus gamma minus substituting this will become minus n plus lambda ln p dash y upon lambda minus kappa, which is equal to 1. Now, rearranging what with the denominators are same, so we can write L lambda ln p dash y minus gamma plus n minus lambda ln p dash y. Now, this and this goes away. What we can write? We can write n minus gamma is equal to lambda minus kappa. So, this relationship comes from here. Now, for the critical state point, this particular point, we can write V kappa minus kappa ln p dash cs, this particular point from the loading unloading line. From the critical state line, the same point can be represented as Vcs equal to gamma minus lambda ln p dash cs. Now, substituting these two, we can write gamma minus Vk is equal to lambda minus kappa ln p dash cs. So, Vy is equal to n minus lambda ln p dash y from this particular equation from the normally consolidated line. Vy can also be written from this particular loading unloading line, I mean to say this particular point. Vy is equal to V kappa minus kappa ln p dash y. Substituting these two, we can write n minus V kappa is equal to lambda minus kappa ln p dash y. Now, from the previous slide, considering the critical state point, we can write lambda minus V kappa is equal to lambda minus kappa ln p dash cs. Now, this minus this will give n minus gamma is equal to lambda minus kappa ln p dash y minus ln p dash cs, and that will give ln p dash y upon p P dash Cs. But we already have derived this particular relationship where n minus gamma is equal to lambda minus kappa. Substituting that, we can write ln P dash y upon P dash Cs equal to 1. This is where we started off with, that this particular relation holds good. So, that we have just now proved that this particular point and this particular point on the P dash axis is related by this expression ln P dash y upon P dash Cs. That is the attribute of this particular yield curve, and hence P dash y upon P dash Cs equal to 2.718. So, that is all some very basic information related to critical state framework in CAMCLA model. Okay. So, the one part is what we have discussed now. So, let us try to summarize this particular portion. We need to understand that this type of understanding we need to develop in steps. So, what we are exactly doing is that adding one by one. So, here for this particular course we need to stop here our level of understanding. Now, the next level of understanding for you will be in terms of plasticity behavior of soil, where both the complete constitutive relationship becomes important, and for which the stress strain in both elastic and plastic framework need to be understood. So, let us summarize today's lecture. The CAMCLA model CCM is a simple and basic elastoplastic constitutive model based on critical state framework. Now, again I would like to use a question while telling elastoplastic constitutive model. We have not completed the entire constitutive model. We can say it is constitutive model when there is a proper relationship between stress and strain. Okay. So, we have discussed the partial framework right now. It defines the state boundary. Now, here our entire effort is in understanding the state boundary surface, and that is fully justified in this type of discussion, and that you will see that whatever we have learned just now, we will understand that in terms of 3-dimensional state boundary surface. So, that part is completely dealt in this particular course, in which the soil exists during shearing. CCM is one of the mathematical representations of the state boundary surface. There are different ways by which it is done. Now, this CAMCLA model is one of such representations. In original CAMCLA, the yield curve is represented by logarithmic spiral. Yield curve correspond to a particular specific volume. When the specific volume change, the size of the yield curve also changes, but the shape essentially remains the same. So, yield curves are identical in shape, but with different size. Size changes with specific volume. Yield curve passes through origin and have 0 gradient where it intersects with the critical state line, and that is at the topmost portion. The equation of yield curve in CAMCLA model is Q by M P dash plus lambda by lambda minus kappa ln P dash minus gamma minus V upon lambda minus kappa equal to 1. And it also holds this particular relationship, that is the yield stress upon the stress at the critical state. It is correlated as ln P dash y upon P dash Cs equal to 1, or P dash y upon P dash Cs equal to 2.718. So, that is all for this particular lecture. We will see the modification of this original CAMCLA in terms of modified CAMCLA framework in the next lecture. Thank you.